Good afternoon all. Start with the today live interactive sessions. It's almost 3. Uh, so what that let the other students be joining in the within the session. We'll start with all the big content and submit the tutorial problems which we are going to solve it today. Okay. So first what I will do is that we'll go through the big content and lectures that has been covered. It's the and during the uh, live interactive sessions during the last 2 weeks. So this is the third week for the live interactive session, and like in the week 1 and week 2 we have discussed related to the fundamentals, the basis of the chemical engineering thermodynamics, uh, some laws related to thermodynamics, that is first, second and third law. And the fourth one that we have discussed is some of the properties like thermodynamic property relationships, Maxwell relationships, and we've also seen some of the numericals in the assignment as well as tutorial problems, and we have solved it during the live interactive sessions in 1 and 2. So today we will begin with the third week and we'll see first the concept that has been covered during the week 3 in the NPTEL swim portal, and then we will go on to solve some of the numericals related to that of the week 3 content, and then we'll wind up for today. So welcome on this course on chemical engineering thermodynamics in offered on the NPTEL online course certification course. So just a quick view. So this course has been offered by Professor Gargi Das from the Department of Chemical Engineering from IIT Kharagpur. And a little bit about myself is that I am Rajput Shivamajikumar. I am a PMR scholar in the Department of Chemical Engineering at IIT Madras. So like I said, I will be your teaching assistant for this online live interactive sessions that is going to be held on every weekend Saturday from 3 to 5 p.m. So we'll be solving all the numericals as well as some of the tutorials and the concepts that have been covered during the entire weekend. Week. And then we'll try to come up with some of the questions and the answers which can be solved during this live interactive session. So what we have been discussing from the past 2 weeks is, like I said, the concepts of thermodynamics, basics, laws of thermodynamics, Maxwell property relationships, thermodynamic web, and like intensive, extensive properties, reversible, irreversible processes, path process, everything we have discussed right now. So in this week 3, the contents are, so this is week 3 of live interactive session. So we have already gone to the week 2 weeks, and all the lectures and the supporting content has been in the form of PDF has been uploaded in the on the NPTEL Swim portal. You guys can go there and download it at the extreme bottom. So if you go to the NPTEL Swim portal, on the like on the bar on the left hand side at the extreme bottom will be like the lecture videos as well as the content. So you can download that videos in the MP4 format and also the content in the PDF format. So what I will be solving during the entire session, it will be uploaded as a PDF. So the PPT will be uploaded in the form of a PDF, as well as this lecture has been recorded for your preferences, and it will be given it to you in the YouTube as well as in the NPTEL Swim portal. The link will be there, so you guys can go and watch and solve any numericals what has been covered during this live interactive session at that time. So the week 3's outline is somewhat like this. The first one that has been covered is related to the Gibbs free energy as a function of temperature and pressure, and the PVT behavior of the gases. So this is like a new concept that has not been related to week 1 and week 2, but it has to be related from the basic concepts of thermodynamics. So why we study PVT behavior, what are the Gibbs free energy functions, and how it is related as a function of temperature and pressure are the concept that has been covered during the week. Okay, so apart from them, there are so many things that has been like yet to be covered from a basic point of view. But what I was saying is that, like we have discussed for the ideal gas equation of ideal gas equations, then in the real world all the concepts that has been related are not based on the ideal, it's based on the non-ideal solutions, the non-ideal gases. Like the ideal gases, there will be non-ideal gases in the real world. So there will be many equation of states. Like in an ideal gas equation, there is non-ideal equation of states. They consist of like 4 different equations: Van der Waals, Redlich-Kwong, Redlich-Kwong, and Pang-Lorentz. So we'll be discussing this in the week 4 and the week 5 as we proceed with the lecture contents. But as of now, we'll be discussing the PVT behavior of the gases and some of like the isotherms and the temperature diagrams for the same, as well as what is the Gibbs free energy. So this content has already been covered in week 3. So what I will show is just the basic outline, how to just identify PVT behavior of the gases and what this the specific terms means about. So if you see this, the first figure actually, so this is taken from some reference book. So I have mentioned here the reference, actually it's in a very light form. Okay, you can go there and check that from a reference book. So The first figure itself shows, if you go look at the first figure, this is figure 1 and this is figure 2. So if you go and look on the figure 1 and figure 2, what is this says is the PVT behavior of pure fluids, example water, and the PT diagram of pure material. So there are two different diagrams. You can't relate both the diagrams in one go. So that's why I've shown in different points, because we have to discuss the PVT behavior of gases also. So PVT behavior of gases has already been discussed. So what I've shown here is that we have to discuss the PVT behavior of liquids or fluids. Okay, so the content that has not been given, I think it's been given in the lecture notes, but I wanted to just emphasize more on the fluids also, because gases has been covered during the weekend. So this is what I've been shown here is the PV diagram of a pure fluid, that is water, at a room temperature. Okay, so if you see, there is an isotherm, and there are three different mixtures of the liquid. The first one is the liquid phase, the second is a mixture of liquid and vapor, like liquid and the gases, and the third is a gas phase. Now, if you see, the pressure increases, and if you keep the volume constant, you keep on increasing the pressure. What will happen to the liquid is that it will try to, because if the volume is constant, if you suppress the liquid will attain the shape of a container, but it will not increase the volume. So if you go on increasing the pressure and the volume, what will happen is that you will reach a point known as a PC and VC, keeping the volume constant, or if you change the volume and keep the pressure constant, there is a point which called as a C. So this point is known as a critical point. So this is the point at which the both the phases exist in co-equilibrium. So if you see, if the pressure reaches a point C, this is known as the critical pressure, that is PC, and if the temperature reaches a point at the like the C, it's called as the critical temperature, similar to the volume. So there are three different terms here that are going to come up, that is critical temperature, critical pressure, and critical volume. And these are how the temperature increases. So if you see, take at the room temperature as T, and if you increase the the room temperature is getting under the critical temperature. So the pure fluid will exit in the form of a gas phase. So this is what we are seeing up here. Okay, and if you say that the temperature is equal, that the room temperature T is exactly equal to the critical point, so the all the three coexist in equilibrium, that is at point C. And if the room temperature is less than of the critical point, so what will happen, it will coexist in two different phases, that is called as a liquid and a vapor. Okay, so this is how the PVT behavior of fluids actually looks like according to this concepts. So the content in the lecture of this has already been there in the like the swim coder. So just go through it and just try to relate how this diagrams can be explained much more in a better manner. So you don't have to mug up any of the like the write up. Just look at the diagrams, how you want, if you increase the pressure, what will happen, how you increase the volume at a constant temperature, constant volume, we will reach at a point as some called as critical point. At critical point, what will happen if you increase the temperature above critical point, below the critical point, what will be the critical pressure and critical volume, and how it will affect the phases present in the system. So this is what it's been related in the first diagram. If you see the second diagram, it shows the pressure temperature diagram of a pure material. So if you take any material that is pure, like the or anything, so how its PT diagram will looks like. So here also there is one point that is called as a triple point. So if you see, there is a point at which all the three phases coexist in equilibrium. So the first phase is solid, vapor, and liquid. So these are the three different phases. So the vapor and gas you can consider one, but it's like a composition of liquid and gas. Okay, so if you say the line which separates in just like simple terms, if you say the separation of the solid and the vapor, which line separates is known as the sublimation point. Similarly, if you can see, the line which separates the solid and the liquid is called the fusion line, and similarly liquid and vapor, that is called the vaporization line. So if you keep on increasing the temperature, the PT diagram of pure material will reach to a point which is known as a critical point. So here there is also a critical point, and beyond that all will be the gas phase. So above critical point, the pure material will exist in the form of gas phase only. So this is like three different terms. So you must remember what is sublimation line, what is fusion line, and what is vaporization line, and what they are is an interface. So these lines act as an interface between the two different phases. So if we take sublimation line, it acts as an interface between the solid and the vapor, If you take a fusion line, it will act as an interface between the solid and liquid, and if you take the vaporization line, it acts as an interface between the liquid and the vapor. And all these phases coexist in equilibrium at a point which is known as a triple point. Okay, and above the critical point, the pure material will exist as only in the gaseous phase. So this is how the PT diagram will look like, and you can explain this in like uh, in just like looking at a diagram. So you don't have to mug up any of the written paragraphs of the books. Just keep in mind how this PT diagram looks like and how you can explain it in your own words. Similarly for the PVT behavior of gases as well as liquids. Okay, so what I will do is that I will write some of the things that have been covered during the week 3 first of all. So this is one of the things, and apart from this, what we have covered is that they have also shown in the week 2 how to calculate the you can say efficiency of the gases and something related to that. So there are like two different things that I think it has to be discussed, although it's not been it's a small portion of the content, but I will discuss it here. So if you see the efficiency, oh sorry, so efficiency of an heat engine, or you can say any heat engine, can be given by eta equal to W upon QH equal to 1 minus QC by QH. So here QC and QH are the heat gain or the heat loss during the cooling and the heating. So C corresponds to the cooling and H corresponds to the heating. And there is one cycle which is called as the Carnot cycle. So the efficiency of a Carnot cycle or engine, you can write it as eta is equal to W by QH equal to 1 minus QC by QS equal to 1 minus TC by TH. So TC is the temperature of the cooling media and TH is the temperature of the heating media, or media in the sense heating sense or cooling sense. So this is like the source and the sinks. There are two different terms. So that will come up at a later point of time. But you should remember what a source and what is sink, what a heat source and what is heat sink. So this is what that has been covered during the Carnot cycle, that is a reversible cycle process, and two isothermal process and two adiabatic processes have been involved in that. So this is already been covered. Apart from that, the various different terms like the entropy. So week 2 content we have discussed related to the entropy related terms. So how this entropy of the process changes, how entropy of the universe goes on continuously goes on increasing. So if you take any adiabatic irreversible process, how you can identify whether the process is isentropic or not. So we have shown already in the week 2 also that we can derive like delta S, that is the change in entropy is determined by integration of dq by t. Okay, and now you can integrate the system, and if you say this is a reversible adiabatic process, so adiabatic process there is no heat flow in and out of the system, so the Q will be 0. Okay, so if this is 0, you can say the delta S of the universe continuously goes on increasing. Okay, so for the reversible adiabatic process, delta S is greater than equal to 0. So this is what we have already been covered. Okay, apart from this, the entropy generated in a flow process. So this can be written as entropy generated in the flow process is equal to delta and dot S Fs minus. So this is I'm writing some the mathematical expressions. You don't have to mug it up. It's just like derived earlier also. And here delta is equal to net change in flow rates, and that is out minus it. So it might looks like weird type of equation as first point of view, but it's like you have to go through all the concepts. It's just like, so what I will doing is that we'll be looking all the equations. Apart from this, I also have like some good things to go through. So once we go through the non-ideal equations, we will see how to solve the equations like ideal gas equation of state, non-ideal gas equation of state, which involves a four non-ideal gas equations using the MATLAB as well as the Excel. So I will show you. You just have to put your data into the Excel sheet as well as in the MATLAB code. You can directly calculate all the isotherms like the PT diagram, TP diagram. Everything can be calculated using that thing. So it's just for like not by them. So by calculating manually the paper, if you want to plot the PT diagram, it will take tons of time for you. It will take entirely whole day also for you. You will not be able to come at a particular point, and then you have to plot everything on the graph plots. What I have done is that I have created a MATLAB code for the same things for ideal and non-ideal equation of state for you guys, as well as I have created an Excel sheet. So in Excel sheet also, so most of guys will be knowing the MS Excel, right? So in MS Excel also, just have to put a data there like the pressure and the temperature, and just write up an equation, and just the entire Excel sheet will calculate the PT diagram as well as the TP diagram or TB diagram, and it will plot it also. So you can calculate and you can relate that data with the NIST database. That is a database which includes all the parameters for the critical temperature, critical pressure, and critical volume, and critical temperature. Okay, so this is Jones. So what I'm trying to say is that don't just look at this equation. This are somewhat weird equations. It's like it has to be go through a part of the chemical engineering thermodynamics. It might come up in some of the questions. That's why I've been highlighting it here right now. So there are much more things to come up the later point of stage, but don't get worried about looking at these equations as of now. So if you see, also we can show at a steady state. The work done in the ideal process will be process, and in this case the change in the entropy generated by the system is 0. Okay, so what I'm trying to say is that at a steady state, what will happen to the entropy generated in the flow process, because the flow will be constant. So what will happen, the work done during the ideal process will be nullified. So in that case, the entropy generation during the flow process in the steady state will be 0. Okay, so this is another point, and one other point, the work. So if I want to write the work lost, so that is the work done and the work lost. So work lost in WM and WS, W ideal equal to T sigma, so delta M S minus Q dot. Okay, and if there is only one uniform temperature, if you take only one uniform temperature, what will happen to this equation is that we try to like simplify this equation. Then what will happen is that W lost equal to T sigma, and it will comes out to be Sg, whereas Sg is in joule per mole Kelvin, and W lost is in joule per mole. Okay, so this is what, just to show you, just yeah. So this is just to show you what has been covered during the week. So there are different equations, different terms that has been covered during the entire weekend. I can't just solve the entire equations. I can solve it, but it will take much more time. Instead, I can focus more on the concepts, the basic concepts, as well as the final equations, so that the equations can be used in the numericals. So what we'll do is that we'll try to solve some of the numericals related to the uh, week 3, that is like what I've shown up you here right now. So what I'll do, we'll start with the question first. So just go through the question first, what has been asked in the question. So if you see, a Carnot engine operates between two temperatures, T1 and T2, that is Q1. So the first temperature is 800 Kelvin and the second temperature is 480 Kelvin, and it rejects the heat at a rate of, that is the Q that is given as 300 kilowatt to a cold reservoir. That is, a heat sink is given and a heat source on the heat sink. The amount of the work done by this engine in kilowatt rounded up to the nearest integer. So this is the simplest question, like what I've been already given the equation before, like the efficiency of a Carnot cycle or a Carnot engine and efficiency during the reversal process. So how you can calculate using that equation? So this is the numerical. So you just have to put that equation here directly. So temperature has been given to you and the heat rate has been given to you. Okay. So this type of question, this is the most simplest type of question that can be asked, and it has been asked in the GATE core examinations for the that is the exam for the PSC as well as getting into the IITs and NITs. So it's easy and quickly to grab for the 2 marks, maximum 2 mark question. So just like you need to remember what is the efficiency and how efficiency is calculated for the Carnot cycle or the heat or sink process. Okay. So if you see, efficiency equal to 1 minus Tc by Th, we already discovered. So 1 minus, so cooling temperature is given as 480 divided by 800, this comes out to be 0.4. Okay, now what we have to calculate is efficiency of all the work done by this engine. Okay, now we also know efficiency is 1 minus Qc by Qh equal to 1 minus Qc by Qh. Efficiency we calculate equal to 0.4. Therefore, Qc by Qh equal to 0.4. Okay, 1 minus 0.4, it turns out to be 0.6. Now if you apply the first law, apply to the energy yields. So if you are applying the first law, so what will happen is that Ws equal to QH minus QC. QH is going to be 500 minus 300. Oh, wait. So what we have calculated here is that till now is from the temperatures we are going to calculate the efficiency first. That is that is eta equal to 1 minus, this is the efficiency, and we know that efficiency is also related to Qc by Qh by this equation. So these two are the equations, and we have Qc by Qh equal to 0.6. Now what we'll do is that Qh equal to Qc by 0.6. Qc is given to us heat rate, heat rejection is given to us, cold system is 300 by 0.6 is equal to, this turns out to be 500 kilowatt. Okay, now applying the first law. So now we apply the first law here. So we have Ws equal to Qh minus Qc equal to 500 minus 300 equal to 200 kilowatt. Okay, so this is the answer. So what has been asked is the amount of the work done by engine in kilowatts. So this is how you calculate simply from the equations of like what I've given up here is the efficiency equations. So this is how 200 amount of kilowatt is the amount of the work done by the engine, which is rounded up to the nearest digits. So we don't have to round up; it's almost coming in hundreds. Okay. We'll go to the second question. So just quickly go through the question first of all, what has been given and what has been asked. Okay, so we'll read the question carefully. So consider nitrogen behaves as an ideal gas. So it's for an ideal system, and nitrogen behaves as an ideal, that is an inert gas, under the conditions of interest. So they have taken a nitrogen gas and they say consider nitrogen as an ideal gas. Okay, its specific heat capacity, that is Cp, for an ideal gas is given as Cp of an ideal gas is 3.5 R. The change in the entropy when 10 moles of nitrogen undergoes an expansion. So the number of moles of hydrogen N is given as 10 moles, and it goes an expansion from T1 to T2 with P1 and P2 that is given off. So we have to calculate the change in the entropy, that is delta S. So what we'll do is that we have the equations, like if you say change in entropy of an ideal gas by R by integrating the equation from T0 to T, Q dt, Q is equal to mCp delta T. Okay, so I'm directly writing the equation Cp by R minus N P by P0. So this is the equation that has been derived and already been discussed in the week 2 cut 10, how the change in the entropy of an ideal gas varies. So this is similar question what we have discussed during the week 2, but this I am taking directly the equation because I know what is the entropy change for an ideal gas and how it can be related to the change in temperature and the pressure if both the things are given, because we see T1 is given to us, T2 is given, P1 and P2 is also given to us, and the specific for ideal gas is given to us 3.5 R. So what we'll do, we'll just write up here. So T1 is 600, 300, 3.5, R equal to dt by T, because RR we cancel out. Okay, so this is R, this will cancel out, minus ln P0. So P0 is initial pressure, it is 6 and this is 3. So this comes out to be this thing. So if you calculate delta S of entropy of an ideal gas equal to, this will comes out to be minus 1.73 into R. R is a universal gas constant. You can put the value as 8.31451 joule per mole Kelvin. So if I multiply with this, what will comes out to be minus 14.41 joule per mole into Kelvin. Okay. Now we have to calculate a change in entropy for the total number of moles. This is for an ideal gas. For a nitrogen, if we have like 10 moles of nitrogen, what will happen is that we will take delta S total equal to delta S of an ideal gas into the number of moles is equal to minus 14.41 into 10 equal to minus 114.1 joule per Kelvin. Okay, because mole will cancel out. This is moles, and we have joule per mole into Kelvin. Okay, so this two will cancel out, and delta S total comes out to be this thing. Okay, so this is what the answer looks like. So this is our answer. So it's just like what I've been saying is that if you know each and every content that has been covered during the week 1 and the week 2, so it's better for you only because you don't have to mug up everything again and again. So because all these questions will be related one after another. It's not like that if every concept will be have their own equations and that all. In chemical and thermodynamics, even the basic equation of enthalpy, entropy, Gibbs free energy, Helmholtz free energy are related to each other. So if you know what is Gibbs free energy, Helmholtz free energy, thermodynamic relationships, thermodynamic web, as well as the Maxwell relationships, it's much more easier to come at this point, because here only, if suppose no one knows this equation, what you can do is if you know the concept of entropy, how entropy changes and how entropy is related to the process for heat. So delta is equal to integration dq by t. So if you get q is equal to mCp delta t, we have Cp is already given for an ideal gas. So you can formulate the equation, you can integrate from the initial temperature to the final temperature, and P can be related to the initial pressure to final pressure. Okay, so this is how we can derive this, because this equation is not a rocket science. It's just if you know the basic equations, you can arrive at this equation also, which in just like 3-4 steps. Okay, so I've shown here directly because we've already been covered in week 2. We have solved like to do the different numericals on the same, but here we have solved it for like somewhat called the total entropy of an ideal gas. Okay, so we'll begin with question 3. Okay, so first we'll see what has been given. So this is similarly like we have given like consider an sulfur dioxide to be an ideal gas. So they have been saying consider an ideal gas which is sulfur dioxide with a heat capacity. So the heat capacity is given to us in the equation at Cp of an ideal gas with this parameter equation. Okay, so we'll use this equation as we proceed to solving the numerical. So they are saying it is heated to in an isobaric. So isobaric process means constant pressure. So these are the different terms that I have covered during the week 1 live interactive session. I have shown what is isobaric, what is isochoric, what is isothermal, what is isentropic processes. So 4 to 5 and what is adiabatic also. So we have seen 5 to 6 different terms that will come up directly into the numerical questions, because if you don't know these 5 to 6 different terms, it will be very difficult for you guys to identify what are these terms and how you can incorporate these terms into your solving the numericals. Okay. So this one is one other term that is isobaric process, and we have been given temperature from 400 Kelvin to 800 Kelvin. Okay. So and they have asked the entropy change in joule per mole Kelvin rounded off to decimal. So this is somewhat like questions that has been asked and been asked every time, mostly every time in chemical and thermodynamics gate examination. Okay. So they will say to round off to some decimal digits. You can use the scientific calculators in the examination also. But if you have like plus like 2 to 3% error will be Q, but not more than like the 5% or 10% deviation from the numerical values. So what we'll do, we'll try to solve it out. Now, like the equation that I have shown previously, we'll take this equation only. So we'll just write out delta S of an ideal gas divided by R is equal to integration T naught to T Cp of an ideal gas divided by R dt by T minus ln P by P naught. Now the one major thing. So if someone don't know what is an isobaric process, so what they will do, they will try to think, okay, how to calculate this term. This is the second term. They don't have any pressure given. What is an isobaric process? How to incorporate this isobaric process in order to know, like, simplify this equation parameters. So if you know that isobaric is constant pressure process, what will happen? This will turn out to be zero directly. If you don't know what is isobaric, then you can't even proceed further into the numerical. Please remember 4 to 5 different terms. Isobaric, that is constant pressure. Isochoric, that is constant volume. Isothermal, that is constant temperature. Isentropic means constant entropy. Adiabatic means constant heat flow. There is no heat flow in and out of the system. That is equal to that is adiabatic process. Please remember these five different terms. It will be helpful for you guys. Okay. So now, so this is because the process is isobaric. So now it will be simplified as So I'm trying to simplify this thing, and what I'll do now, that we have been given Cp by this term we have been given to us. Okay. So what we'll do, we'll directly take from this point. So we'll try to put this one. Or what I'll do is that instead of putting this one, because I have to integrate this one also. So what I will do, I will just put in the form of a like some order a plus bt plus d by t square into dt by t instead of writing the entire term. So what I will do, I will try to integrate this one now. So what will happen? This will comes out to be a ln of t by t naught plus b t minus t naught minus t by 2, yeah, 1 upon t square minus 1 upon t naught. So this is just for like simplifying the equation, so that I don't want to put the entire numerical terms here like 5.68 because in examinations many of us will make errors, and I'm 101% sure that all of you will make errors by putting this value and integrating it with the initial temperature to find temperature. So what you can do, you can just take some of the like assumptions, like suppose 5.699 is A, B is 0.801 into 10 raised to minus 3, and T is that already been given here, and C by d by t square. So d is 1 point minus 1.05 into 10 raised to 5. Okay, now just integrate this term and put those values now in this terms. So what will happen? I will try to put this term. So A is 5.699 ln of. So we have been given T1 and T2. So what is, so T is the final temperature, that is 800 by 400. That is B is 0.801 into 10 is to minus 3 into 800 minus 400, and D is given to us as 1.015 into 10 is to 5 divided by 2, 1 upon 800 square minus 1 upon 400 square. So this is like what, if we simplify, it's very much easy to solve at a final point. So if you solve this point, what you will get is delta at of Ig equal to, just use scientific calculators, you will get a value of 4.03, and we'll take this R on the right hand side, so it will multiply by R, that is 8.31451 Kelvin. That turns out to be 33.53 joule per kilomole Kelvin. Okay, so this is like the simplest questions. Just you need to know why to integrate, what is the different terms that has been given in the questions. Okay, so if you don't know, it will be difficult for you guys only. So don't try to mug up any of the terms. I'm saying it constantly, and every time I'll be saying till the end of this course, till April, that don't try to mug up everything. If you try to mug up, it will be difficult for you guys only to relate some of the things that you don't even know. Okay, just go to the basic concepts. So like what I did, I remember what is entropy and how, what is this equation, how to arrive at that equation, and then I formulated, okay, there are different temperature and pressure given. I will integrate the equation to different limits of T1 and T2 and P1 and P2. Then I write at this point, and now the process is isobaric. That means the pressure is constant. So I don't need to go further. I will just cancel this term, and I try to simplify this term. Now since specific has been given to us, I will take directly into this equation. I'll try to integrate. But even by integrating, I see that this equation is given to me very large. So by integrating this one, what I will find is that there will be some mistake in plus and minus or integers that will definitely make. So I try to simplify in form of A, B and C and integrate this, and then I will try to put up the values directly in there. Okay, so that is what we did, to simplify the equation, and we'll try to put up the values. So this will be much more helpful for you to, in the like the future also, like in some of the numericals that will come on the exams also. If the integration looks too much complex, try to break it down into two different or multiple different parts. Suppose you try to solve this part specifically, and in that specific part, if the numerical values are too big, try to split this big value into A, this big value into B, and suppose this value into C, and just try to integrate that with the limit that has been provided. So what will happen is, once that is integrated, only you need to put that values directly at the simplified equation, because putting directly the values and integration, it will make a messy situation for all of you. So it's better to make some assumptions and try to integrate that assumptions, in the sense, just take like that numerical values, it signifies A, that technical values simplifies P. Try to integrate A with respect to dt2. So what will happen? A into t square, like t is to n plus 1, so A t square, and put the limit of t square t1 to t2 and try to integrate that. So this is the most simplified way and easiest way to solve the integrations. So those who find this integrations difficult, it's not that much tricky. You just need to think and like put your own efforts now to simplify the equations. So that's the key point in solving numericals in chemical engineering thermodynamics, how you can simplify. Okay. Yeah. We'll go to the question 4. We'll see what has been given in the question 4 first of all. So methane behaves as an ideal gas. So here also so until now we have been discussing only on the ideal gas. There will be another concept that will be coming up in the like week 4 or week 5, that relates to the non-ideal gas equation of states as well as non-ideal liquids. Okay. So till now we're only doing the first starting part, that is related to the ideal gas and ideal liquids only. We'll come off in the later point the non-ideal equations, and that are called as the equation of states as well as on the non-ideal liquids. So it has been given that consider ideal gas as a methane and the conditions of interest. If it's compressed in a steady flow, the time is constant. Steady flow process a rate of 3 mole per second from 1 bar to 50 bar and T1 to T2, that is 300 Kelvin to 400 Kelvin. So we have been given P1, P2, T1, T2, and the rate of compression is given as a rate of 3 mole per second. The surrounding are also as 1 bar and 3 bar. Okay, so the surrounding pressure and temperature is given to us this. So we take as P surrounding and temperature of the surrounding as 1 bar and 300 Kelvin. The average specific heat capacity of methane under these conditions may be assumed to be okay. So the specific heat under this condition, that is under the ideal gas conditions, have been given to us 38 joule per mole Kelvin. The minimum amount of the work, that is kilojoule in second, required or necessary for this compression will be. So need to find out the work done on the ideal gas, that is methane, uh, under steady state process in kilojoule per second. So we'll just start with it. So here there are two different things that you need to identify first of all. So here what I've been given in a flow process, the ideal work is given, and since the work is done on the system, so there are two different types of work done on the system, work done by the system. So if work is done on the system, there will be some nomenclature in the sign convention, there will be positive or negative. So you must have to take care what is positive, what is negative, work done on the system and work done by the system. So we will write ideally work done during the ideal process So this is the equation that I have already written. So what we'll do, we'll first calculate enthalpy change of an ideal gas. So it will be integration T0 to T Cp of Ig dt by T. Similarly we need to integrate this equation. So if you take Cp of Ig, it is given to us as 38. And T1 to T2, if you integrate, if it's given at T1 is 300, T2 is 400. So T2 minus T0 will come 400 minus 300. This comes out to be 3800 joule per mole. Okay. Now what I will do, the entropy change in the ideal gas first of all. So the equation that I have already given, Cp of Ig dt by T minus RLN P by P0. So this comes out to be 38 ln T by T0, that is 400 by 300 minus R is 8.314 51 joule per mole Kelvin, ln of P2 by P1. So P1 is given as 1 bar and P2 is 50. So this is P1, this is P2. So P0 is the initial pressure and P is the final pressure. Okay, so we'll write out here also. So we'll try to solve this equation. It turns out to be okay. Now what you have to find out is the work done. Work done during the ideal process is equal to N So enthalpy we have found out is just 3 mole per second into enthalpy we have found out as 3800. So it's 3800 joule per minus temperature, that is at 300 into 3 mole per second. So this is in Kelvin into entropy change during the ideal gas. This is the enthalpy change during ideal. This is entropy. This is minus 21.59 joule per. So this comes out to be 30.833. Okay, sorry, this will be 30,000 actually, because there is 3800 minus 29.59 and it's multiplying by 3. So it will be in thousands. So if it comes in, so what has been given, they have to calculate kilojoule per second. So convert in kilojoule. So 30.83 kilojoule per second. Okay, so this is the answer. So this is the not like the more tricky one, but like the simplest one how to arrive at a point. So we will just derive from the entropy change of an ideal gas, entropy change of enthalpy change of an ideal gas. So if you know what is an ideal gas and ideal gas systems, and if you know how to relate that equations with the parameters like T1, T2, P1, P2, specific heat. Okay, so this is the basic equations you might be knowing after the concepts of entropy, enthalpy, everything. So if you don't know these things, it will be difficult for you only. So that's what I'm saying. Don't try to mug up anything. If you go on mugging up everyone, you will be lost at the end. Okay. So this is the question 4, and this is question 5 on the numericals. So I'm trying to cover as much as I can because I don't want you guys to just like go through the concepts. You have to solve the numericals. Unless and until you solve the numericals on your own, you will not be able to identify how can I use these concepts on the applications. Because looking at the concepts and mugging up the concepts is easy, but once it comes to solving the numericals, it's not as an easy point, easy peasy job. Okay. So this is the question 5. We'll just go through what has been asked and then we'll try to solve it out quickly. So if you see, consider a steam turbine that accepts saturated steam at temperature given to us at 473 Kelvin and at a rate of 2 kg per second. That is a flow rate that is given to us at 2 kg per second and it's a temperature of 473 Kelvin. At the exit of the turbine, liquid water of temperature 333, that is 333 Kelvin is obtained. The enthalpy and entropy changes for the working fluid from the inlet to the exit of the turbine are this. So the enthalpy and entropy change has been given to us as this is the enthalpy change, this is the entropy change. Okay. Consider surrounding to be at also. So the surrounding is also at 333 Kelvin. The turbine operates on a steady state. So this is one condition, that is the steady state. There is a constant time. And efficiency is given to us with an efficiency of 60. So this is eta. The absolute value of the lost work. So this is not the work done, but the lost work we have to find out to the nearest value. Okay. Then what we'll do is that, so this is similar terms. So we know that work done in the ideal is equal to delta H Fs minus T sigma delta n dot S. So this n dot S is not the number of moles involved during the change in the enthalpy and entropy. So the enthalpy and entropy change has been given to us. So this is first is enthalpy, second is entropy. So first is minus 2540.8 kilojoule per kg into delta. So number of moles that have been given to us as the flow rate is given to us 2 kg per second. Okay, so this is has been given to us, and T is given to us as 333 Kelvin, 333 Kelvin. Into 2 kg per second into minus 5.6 kilojoule per kg Kelvin. Okay, so this is what has been given to us, and I'll just directly put in this equation and try to solve it out, or just like to simplify with the help of scientific calculator. The work done by ideal process will comes out to be 13 1.52 kilojoule second. Now the turbine does not work on the surrounding. It's operated as an efficiency of 60%. So we have been given an efficiency of 60%. That is, the turbine operates at the efficiency of 60%. So now we know efficiency is equal to work done during the actual process by work done during the idle. So we have actual work done comes out to be efficiency 60%, so it comes out to 0.6, and the work done during the idle process comes out to be 1352. Okay, sorry, here it's like 3, right? So it comes out to a minus. Okay, so minus 1352. This comes out to 0.6. No, the thing that has been asked was the work lost of the work in kilowatt. We have not been asked the actual work done. We have been asked the lost work. So what we'll do, we'll write W loss equal to W idle minus W actual. This comes out to be 540.8 kilojoule per second. So this is how, like, the terms that I have shown you, and how you can relate with the concepts that we have discussed starting on this live interactive session. Okay, so the only thing you guys have to remember is a change in the entropy, change in enthalpy for an ideal gas, how you can incorporate that equations using the different temperatures and the pressures. So if you try to integrate that thing with the temperature and pressure, you will arrive at a particular point where you have that equation. And how you can relate that thing with the efficiency of the system. If you say that if it's an ideal system, what will the work done during an ideal gas system, what will the work done or work lost during an ideal system, and how you can relate these equations with each other. So it's just like interrelated concepts, but if you don't know what is enthalpy and entropy, it will be difficult for everybody. So what I've been trying to say again and again is that just try to solve these questions on your own once. Don't try to look the just go through the concept once. Take these questions, try to solve it out on your own. Just don't look at the solution that I have been solving up here, because if you look at the solutions, you will know, okay, this is the solution that I can solve in this manner. Just try to look at the concepts that I have discussed today in the starting of the session, and just go through all the numerical questions. There are 5 numerical questions we have been solving today. So what will happen is that once you know the concepts and the questions, you will try to solve it. Your brain will try to work it out. Okay, these are the concepts. I just like to implement some of the numeric like the equations here, what has been given, and the different points of time. So once you solve it on your own, you'll get much more confidence instead of looking at the equations and what I'm solving in every class. So it's good for you only, not for me. It's for your betterment. So what I will do is that this everything will be uploaded on the NPTEL Summit portal, and the videos also will be there. But what I will suggest is that try to solve it out on your own first. If you don't know, then you can go and look at the solutions for the further point of time. Apart from this, we will see some of the MCQs related to the concept terms that has been covered. Okay, so as of now, what I've been doing is that I've been solving all the numericals, and in exams there will be like different MCQs also. It's not just like solving the numericals. There will be MCQs also related to the simplest one marks MCQs. In the gate examinations also there will be like different like the marks distribution will be such that chemical engineering thermodynamics is there. It will be distributed into 8 to 10 or it varies year to years and varies according to the IITs who prepare the questions paper every time. So the main content for the chemical engineering thermodynamics weightage will be varies from 8 to, like, I can say from 8 to 12 different 8 to 12 marks for the entire course for the chemical engineering thermodynamics 1 and chemical engineering thermodynamics 2 for the entire undergraduate course of chemical engineering thermodynamics. So it's like a higher weightage similar to like other courses, the core chemical engineering courses. So and it's easy, not that much hard. The only thing is that here you need to remember the concepts. It's not like mathematics. You'll try to solve it and you arrive at an answer. So here in thermodynamics, if you don't know the concepts of thermodynamics and which concepts has been applied specifically to that numerical to arrive at a point, it will be difficult to grab the marks. So we'll solve some of the MCQs here for this session. So if you look at the first point, the change in the entropy, like we have been discussing entropy change from the past 2 weeks. So entropy change, enthalpy change, Gibbs free energy change in the Gibbs free energy and entropy. So like some numericals will also come in the final examinations also, and it will also be there in your assignments. So once the assignment due date is over for the week 3, we'll try to discuss that one also. So we already discussed week 1 and week 2 assignments, but I'm not discussing because week 3 due date has not been ended for the assignment. So when it's over, we'll try to solve that one out also. So here in the first numerical, if you see the relation ds equal to dq by t is valid for. So this is I've been saying from the beginning of the lecture, how you can relate change in entropy with the heat and temperature. So I already told the answer also in between the solving the numericals. So if you see ds equal to dq by t, and it's valid only for a process of called reversible adiabatic. Okay, and this is irrespective of the any type of the process. So this equation has been solved keeping in mind that the process is reversible. Okay, so if you can, what we'll do is that it will nullify two of the like the options directly. So this will not be an option, this will not be an option. The only thing is that reversible or an adiabatic reversible process. Now there are two different terms. Like if I say if an adiabatic reversible process, the equation comes under constant entropy process, that is ds comes out to be greater than equal to 0. Okay, but what I've been given is that this equation is valid for, as of now, in the process they have been given in the question, so it's valid for only for a reversible process. If I say the process is reversible and it's adiabatic, so what will happen is that adiabatic process means q equal to 0. So this is for an adiabatic process. There is no heat flow in and out of the system. Okay, so if q tends to 0 or q is equal to 0, there is the process is adiabatic, there is no heat flow in and out of the system. So what will happen is that ds equal to dq by t, this comes up to 0 and ds equal to 0, and we mostly say the entropy of the universe goes on increasing, so it will be greater than equal to 0. So if in general the question says ds equal to dq by t is valid for a reversible process, and if we say if it's how we can relate the equation to the reversible adiabatic process, so what will the process terms? So it's called as an isentropic process. Let's say entropy is constant, that is isentropic. So relates the change in the entropy is 0. Okay, so please remember these points, like the simplest points. There will be there in the form of MCQs in the gate question exams also, as well as in the final examinations also, as well as in the assignments. So this is the correct answer, like what I've been explaining, an irreversible process, because it's valid only for a process where the process is irreversible irrespective of the type of the process. It doesn't matter what is the process, but it's valid only for the process which is reversible. Okay, we'll go to another question, a similar MCQ. So for an ideal gas undergoing an isothermal process, so like the previous term, like I said, is in a constant entropy process known as isentropic. Now constant, what is this isothermal? So it's related to the constant temperature. So if you say your process is that is an isothermal process, so what you can say is it's performing at a constant temperature process. Okay, so now here what has been given and asked to us is what is a for an ideal gas. If you have a gas, suppose if we say I will give an example of nitrogen, which is an inert gas. If I say assume this as an ideal gas, and if it's undergoing an isothermal process, that is a constant temperature process, the change in internal energy delta U. Now this can be related to the equation, because internal energy is a function of temperature only. Okay, so this is a function of temperature only. This is an important point. that has been covered in the week 1 content. Okay, so if you see this, if the process is an isothermal and then internal energy is a function of temperature only. So if temperature is constant, because we have been given as a constant pressure process, so what will happen? Delta U equal to 0. So the correct answer is this one. And if you don't know that the internal energy is a function of temperature, then it will be really difficult for you to just quickly, because this is just like within like 10 seconds you can find out the answer quickly, because if you know what is internal energy and how you can relate with the temperature and pressure, and if its process is given as constant temperature, it's just within like 5 to 10 seconds questions. It's just grab easy 1 mark. Okay, so given the explanation here also, for an ideal gas, internal energy is a function of temperature, and as the temperature is constant for an ideal thermal process, delta U will be 0. So the correct answer is A. Okay, so this is the simplest points that please remember. Don't try to mug it up everywhere. Just remember the basics one, which I've been trying to cover during the starting of every live interactive session, so that at the end point, once we go to the numericals and the MCQ that I'm trying to show in every interactive session, it will be helpful for you. Okay, you will be remembering, yeah, this has been covered during the starting of the session, and at the end we are trying to solve some of the numericals as well as the concepts related to that concepts only. Okay. Now this is one different question. So now, since I will not cover this one right now, because I will not explain what are van der Waals equations, but I have shown up here because most of the real world problems are not related to the ideal. Ideal system does not exist in the real world. So every problem that has been solved in the real world, or the industries like oil and gas industries, agriculture industries, pesticide industries, or glass industries, cement industries, all these problems are related to the non-ideal systems. That the system is not ideal. It will have some variation in the temperature and pressure as well as in the volume, and there will be many more variations that is going to happen. So you can't say your system is ideal. Ideally, it should be non-ideal systems. Okay. So for that non-ideal systems, we require different equation of states. So for an ideal gas, we have an ideal gas equation that is equal to PV equal to nRT. Okay. For non-ideal equations, we have like equation known as van der Waals equations. So Redlich-Kwam, and Peng-Robinson. So these are non-ideal equation of states. Okay. So just so what I will do is that we'll try to solve the second part at a later point of time, and I will discuss all the non-ideal equation of states. As of now, we'll just try to go with what are the ideal gas equation and how to solve it this term. So what has been given as the molar volume of, compare the pressures given by, okay, occupies a volume. So for an ideal gas equation, I'm trying to solve only first one. And therefore, PV equal to nRT and P into V equal to RT. So P is equal to RT by V, that is the molar volume, and R is equal to ideal gas universal gas constant, that is 8.31451. Temperature is given as 313, and molar volume of 0.381. This is meter cube. We'll try to joule per mole cabin. Okay, we'll convert into liters, so it comes out to be into 10 to -3. Okay, so this comes out to be 68.30 into 10 to 5 joule. It can be Newton per meter square. If you convert into bar, so 1 atmosphere is 10 to 5 bar, it comes out to be 68.30 bar. So this is the pressure. Okay, so similar thing can be calculated using the van der Waals equation of state, that is related to the change in the volume, because in ideal gas you will see that the volume is constant, the volume occupied by the system is constant, so it doesn't have any parameter. Whereas in van der Waals equation, we relate the non-ideal gas. This is called a van der Waals equation of state. We will occupy for two different terms. One is the volume, and within the space. So the volume occupied the system varies, and there will be two different constant, that is P V minus B is equal to RT by T squared. So you can simplify that equation also. So that is called the Van der Waals equation of state. I'll just try to show you the solution for this. So first one we already solved. So this is called the Van der Waals equation of state, and there are two different constants which are known as the Van der Waals constant, that is A and B. So this you will see once I will try to solve out what are the non-ideal equations and how why you are doing with the non-ideal equation of states. Okay, so this is just the simplest and the number one non-ideal equation of state, that is Van der Waals equation of state. Apart from this, we have like three different EOS related to the non-ideal system, that is Pang-Robinson, uh, Sawyer-Edgecombe, and Edgecombe. Okay. Okay, so this is like, so what the question that has been asking is to really compare the pressures. So how the pressure values will vary if you take an ideal system and a non-ideal system and you try to solve it out using the two different equations, whether it's an ideal gas. So if you take an ideal gas equation of state and you consider the same gas as a non-ideal gas, you will try to solve it out with non-ideal equation of state. So there are three different equations also, like this one, 2, 3, and this is the fourth one. Okay, so we try to solve out or calculate the pressure with all different four or five, these five different equations. The pressure values will vary because each and every equation of state will have their own you can say assumptions and the calculations, and the different parameters values, like the parameters of A and B will be different, will have like different specified values for both of like all the different equations. So you can't say the pressure calculated by the Van der Waals equation of state will be similar to that of the Edgecombe or Sawyer-Edgecombe, and similarly for the Pang-Robinson. It will be different because the parameters A and B will be different in all the cases, and there will be different more values coming up. That is called like the completely spherical shape. So if you I will discuss in the later point of time because I don't want to like try to confuse you guys more if I will not discuss as of now. So we will try to solve it at a later point of time for the non-ideal. As of now, you can go with the Navier equation of states. Okay. So this is how like I solve PV is equal to nRT, and if you take number of moles to volume minus number of moles, it will be the molar volume. So we'll just try to tick all the values, and 68.30 bar. Okay. So another question. So what I've been asked in the given question is that what is the critical pressure of CO2 gas if the reduced pressure at 14.28 atmosphere is this. Now there are two different terms that we have shown and discussed in week 1 content also and week 2, that is critical pressure and critical volume and critical temperature. Okay, CP, CV, specific heat and constant pressure, specific heat and constant volume, and similarly the critical pressure and the critical temperature. So we know that critical pressure is equal to P by PR. Okay, so the critical pressure is the pressure, actual pressure divided by reduced pressure. So we have been given that PC equal to P by PR. Reduced pressure is given to us. If the reduced pressure is found in 2 atmosphere is 0.196 and P is given to us 14.28. So what you have to do is just calculate the reduced pressure is 14.28 divided by 0.196. This comes out to be 72.86. So this is the simplest point. What is critical temperature? What is critical pressure? If you know everything, just it will come directly within one mark question. So this like this specific term like critical pressure and critical temperature will not be given to you in some of the numericals, and if you need to calculate that one fast, then your further numerical solutions can be derived. So why I'm showing up here what is how to calculate critical pressure is that in the next weekend in next live interactive session we will be solving some of the numericals where you have to directly calculate critical pressure in the numerical first, and then you will go to further proceed for the final solution. Because in that question they will not ask you to calculate critical pressure, they will say to calculate directly the final answer. Okay, and at that point of view you don't know how to calculate critical pressure. So that's what I'm showing, how to calculate critical pressure and how it's related to the reduced pressure and the actual pressure. Okay, so this is the equation, and the concept for this has already been shown in the class. So I don't want to just show the concepts. Instead of that, I will try to solve the numericals. It will be much more interesting to you guys as of now. Okay. So like I said, the critical pressure is related to the actual pressure by PC is equal to P by PR. So like what I've been shown here, PC equal to P by PR. Okay, and the correct answer is D. So the last question for today. So just try to go through the questions what have been asked. So if the specific internal energy, that is U, of a substance is given by the equation U in kilojoule per kg is this. So we have been given U equal to 201 plus 0.482 T, where temperature is in Kelvin. What is the value of CV, that is specific heat at constant volume, has been asked to us. So we know that Cp and Cv is the specific at constant pressure, and Cv is the specific at constant volume. They have been asked what is this. So what we'll do, we have know that Cv is equal to del U by del T at V. That is a partial differentiation of the internal energy with respect to the temperature at constant volume, because specific heat at constant volume is given to us. Okay, so what we'll do is that just try to integrate 201 plus 0.482 T del by this by dt at constant volume. So what will happen if we try to integrate this one? So this is a constant term, it turns out to be 0, and this is T and T, so it will turns out to be 0.482. It is constant volume we have to find out. So this is 0.482 and the value is kilojoule per kg Kelvin. So this is just nothing, is just we need to know what is specific heat at constant pressure and what is specific heat at constant volume. So we know that Cv is equal to del U by del T at constant volume. Okay, so just try to partial differentiate it. The first term will be 0 because it's a constant term. We have to differentiate with respect to the temperature, and the second term is related to the temperature, so it will turns out to be 1. So the final answer is 0.482. You don't have to solve it also, just look at this equation directly. So Cv is equal to del U by del T at a constant volume. So just try to integrate this one, it turns out to be 482 because T del T by del T will be 1. Okay, so del of, if you take 0.482 T by del T, so what will happen? T is constant, 0.482 constant, del T by del T will be 1. So the final answer will be 0.482 only. And this term is 0 because there is no variable related to it, the temperature variable. Okay, so direct answer you can say it's 0.482. Simplest form. Similarly, if the question has been related to the specific at constant pressure, you can try to solve it out in the same way. Okay, so I've shown here only that is Cv is equal to this thing and directly the answer. Okay, so this is what I have for today, like solving some of the numericals, and like we have seen some of the concepts related to like the enthalpy change in the enthalpy, change in entropy, and how you can calculate the efficiency, as well as the work done during the reversal process, work lost during the process, work done during the process, or work done on the system, and some of the MCQs related to the concepts that I have discussed during the starting of this session. Okay, so what we'll do in the next upcoming lectures is that live interactive session, and that is on the week 4 result. We'll go through some of the non-ideal gas equation of states what I've shown today, but we have not solved because the concepts has yet to be covered during the weekend. So in the next week, in the week 4, we'll try to cover it up also. So we'll solve some of the numericals related to non-ideal gas equation of state. We'll try to first see what are non-ideal systems, why we want to consider non-ideal gas or non-ideal systems, what are the different equation of states we want to use in order to solve the problems of non-ideal systems, and then we will try to show you some of the coding terms, like in the MATLAB coding. If you try to fit that equations directly, you just have to put your values directly into the MATLAB code, and thus the MATLAB code will directly calculate all the data. As well as if someone does know the MATLAB coding, then we have an easier way to calculate all the pressure, temperature, and the pressure volume diagrams using the non-ideal gas equation of states in the Excel sheet also. So this is the simplest way. Just you have to put your equations in an Excel sheet. We'll try to show you in the next upcoming live interactive sessions. In the meantime, if you have any questions, anything, just feel free to ask me anytime at any point of time. So if you don't have any questions, we'll meet next weekend on Saturday from 3 to 5. If you have any questions, you just try to put up on the NPTEL Swim portal, or you can just mail them, because all these lecture notes in the form of a PDF, what we are solving in the live interactive session, as well as these videos of in the Google Meet, will be recorded and will be uploaded in the Swim portal as well as on the YouTube. So you don't have to worry about anything. You can go at any time, just look at any time to the numericals what we have gone through, as well as the concepts. Okay. So if there are no questions, we'll meet next time. If you have any issues, please let me know on the Swim portal. Or you can drop a message, or you can give a feedback on the NPTEL Swim portal, as well as on the there will be a feedback forms coming up every weekend, like after the week content has been over, as well as for these live interactive sessions. You can give your feedback there also. If you have any issues, please do let me know in between the lectures itself, so that we'll try to solve it every numericals, every questions within this interactive session, so you don't have to worry about waiting for the another weekend to come up. Okay. Till then, if you don't have any questions, we'll meet up next week. Thank you guys for joining this live interactive session for today.